Welcome to MultiCampus Engineers Hub, for your destination for engineering learning.
Welcome to The Explainer. Today we're talking about something that's all around us, a silent, relentless force that shapes our world from the ground up. We're talking about corrosion. So the answer's pretty obvious, right? It's corrosion. You've seen its handiwork everywhere, on a rusty old bike, a forgotten car, maybe even that beautiful green roof on a historic building. But today, we're not just going to look at what it does, we're going to get into the nitty-gritty chemistry of why it happens in the first place. All right, let's dive in. To really get a handle on this, we need to start with a clear, scientific definition of what we're actually dealing with. Okay, a couple of words in here are absolutely key: unintentional and undesired. See, this isn't a process we want to happen. It's a breakdown, a degradation, that always kicks off right on the surface before it starts working its way deeper, really compromising the metal. And this right here is the best way to think about it. You know, we put a ton of energy into digging ore out of the ground and refining it into shiny, useful metals. Well, corrosion is basically nature trying to press the undo button on all our hard work. So that leads to the big question, right? Why is this process so, unstoppable? The answer, like with so many things in chemistry, all comes down to energy. Think of it this way. The refined metals we use for, everything are packed with energy. They're in a high-energy, unstable state. We've basically charged them up. On the flip side, their natural form, the ore in the ground, is low energy and super stable. It's kind of like a ball sitting at the top of a hill versus one that's already rolled to the bottom. And that's the bottom line. Corrosion is a spontaneous process. The metal is always looking for an opportunity to release all that pent-up energy and just get back to its comfortable, stable, low-energy state. It's like a stretched rubber band. It just wants to snap back. It's not evil or anything. It's just physics. So, okay, it's a natural process. Big deal, right? Well, let's talk about why it's a very big deal, with some major and often very expensive real-world consequences. The impact is just huge. It weakens the very structures we rely on, from bridges to pipelines. The economic hit from constantly having to repair and replace things is in the billions. Not to mention, it can lead to some really serious safety and environmental problems when things fail. Okay, let's look at a few of the different faces of corrosion. I guarantee you'll recognize these from your day-to-day life. And here it is, the celebrity of the corrosion world. The one everybody knows and loves to hate, that flaky, reddish-brown stuff we call rust. Now, what's really fascinating here is just how simple the recipe for rust is. You just need three things that are pretty much everywhere: iron, oxygen from the air, and a little bit of water. Mix them together, and you get hydrated ferric oxide, the proper chemical name for rust. If you've got any silver at home, maybe some jewelry or silverware, you've probably seen it get that dull, dark coating over time. Well, guess what? That's corrosion too. But for tarnish, the recipe is a little different. The main bad guy here isn't just oxygen, it's hydrogen sulfide. That's a sulfur compound that's in the air, and it reacts with the silver to create that signature black film of silver sulfide. Think about the Statue of Liberty. That incredible green color, that's not paint. That is a type of corrosion called a patina that's formed on its copper skin over more than a century. Yeah, the recipe for this patina is a bit more involved. It's a really slow dance between the copper and a whole cocktail of stuff in the air: water, carbon dioxide, oxygen, you name it. Over time, they form this layer of basic copper carbonate. But here's the really cool part. That green layer actually protects the copper underneath it, which is a little clue for what we're about to talk about next. This is a fantastic question. This is where the story of corrosion gets a really interesting twist, because sometimes the problem can actually be the solution. This right here is the secret to aluminum's superpowers. The moment aluminum hits the air, it corrodes. Instantly. But, and this is a huge but, the stuff it creates, a super thin, tough, invisible layer of aluminum oxide, forms a perfect seal over the surface. Exactly! The corrosion literally becomes the cure. That initial, super fast corrosion creates a suit of armor that's non-reactive and shields the rest of the metal from any more damage. It's just an incredibly clever bit of natural engineering. So finally, let's just quickly look at how scientists basically split all these different reactions into two main groups. In the end, it all boils down to one of two things: dry or wet corrosion. Dry corrosion is a direct chemical attack, maybe from hot gas on metal. But wet corrosion is way more common. It's an electrochemical process. The easiest way to think about it is like a tiny microscopic battery forming on the metal's surface. That's what's happening with rust, since you need water. And knowing which type you're dealing with is everything when it comes to stopping it. So there you have it. Corrosion is just a fundamental force of nature, driven by the laws of thermodynamics. We can't really stop it. The real question, the whole challenge for engineers and scientists is, how do we manage it? How do we slow it down? And that, well, that's a story for another day.